Okay, now in this video we will be talking about FABMAP. And FABMAP stands for Fast Appearance Based Mapping. Fast Appearance Based Mapping. And obviously this is the technique used for localization and mapping. And what is the main idea? Same. Okay, so main idea is some combination of words co-occur. Talking about this board, if you detect features in this particular frame that you are currently seeing, obviously you will detect corner here. And if somehow we can make the model intelligent enough to understand that if a corner is present here, then it is obvious that a similar corner will be present here, here, and here as well. This feature is called some combination of words co-occur. And word means obviously the features. We call the words in bag of words. What were the words? Obviously the same descriptors or the features that you were extracting from the environment. So this is the main idea. Okay, some features co-occur, and this thing improves the inference at test time, or this improves the inference by reasoning. You will see how. This is based upon bag of words, but the difference is unlike the shift feature that we were using in previous video, here it uses surf descriptors to construct bag of words. Now, it is solution to FABMAP is solution to recognition places. Okay, now you can recognize the places more efficiently. And second, now you can know, okay, have you visited the same place before or not? This thing is called loop closure. Now it is easier to check whether the loop closure is whether the robot is on loop closure or not. And last, based on learning generative model. So it is based on learning generative models, and we'll see how or like why we are saying it is based on generative model. By generative model, it means it generates something out of its own. This ability is present in FABMAP, and we'll see how and where. Okay, so let's talk about working. For example, you have taken an image and there were different features in it. Okay, and your first image was your first observation, and there were different features inside it, and obviously the features can be represented as a random variable. Okay, in every observation the features can either exist or cannot exist, and there is obviously this is the stochastic behavior. It can either exist or not. You don't know, like it is not deterministic. So this thing can be written as this. Okay, this thing, if z1 is first descriptor, z2 is second descriptor, z3 is third or feature. Okay, and every feature we are saying here is a random variable. So the observation, which is z, is the set of different or multiple random variables. Okay, so one observation consists of different features, and each feature is a random variable. So the whole observation is a set of multiple random variables. Now every random variable is independent with each other, and our whole idea is to learn the parameter for z, capital Z, which is very difficult. Why? Because you have to estimate the parameters of each of this random variable to estimate the parameters of this whole distribution, which is very difficult. And plus, storing this information is also very difficult. Why? Because it space needed to represent this increase exponentially with respect to n, where n is the number of descriptors. Okay, so in every frame new descriptors might come, and here this vector is increasing, and so your overall space needed to represent this is also increasing. But we can make this thing like this behavior is called, it is intractable. You cannot track, you cannot like easily or efficiently process everything if all the features are independent. So here we need to represent this same distribution with another distribution, where so that the random variables in the other distribution are not entirely independent with each other. Okay, it depends. Okay, some of let's say features depends on other features as well. So this is where this co-occurrence thing come. We somehow want to learn this, that if z1 is present or if this feature is present, it is obvious that z2 or z3 or z4 will also be present. If z1 was this corner and 2, 3 and 4 was these corners, then it is obvious that if z1 is present, all remaining 3 corners will also be present. This behavior is called first 3 random variables here are now dependent on each other. You don't need to predict every feature. If you have predicted z1, it is obvious that remaining are also 1. This thing is called some variables, some random variables are dependent on each other, and which is not the case here. We need to represent this same distribution into another distribution where this thing can happen, like where the random variables are dependent, and we need to make sure that these two distributions are not too much different. Obviously we will lose the whole point here. We need to make sure that these two distributions are same, but here in this distribution random variables are no, every random variable is not independent. Okay? And this can be checked with KL divergence rule, which gives 0 if two distributions are similar. So we will make an other distribution and we will find its KL divergence. If KL divergence is 0, it means both the distributions are similar. Okay, this is the criteria to check whether two distributions are similar or not. And our goal is to make another distribution where random variables are dependent, but we need to maintain this as well, that these two are similar as well. So this is again an optimization thing. We want to make random variable inside it dependent, but along with that we also want these two to be same. So obviously we will check this through this. We will estimate another z, we will estimate another distribution, and then we will check whether this one and this one are equal or not, or similar or not, so that we can use this distribution for the remaining process. Why? Because the random variables inside this are dependent and are, like we have learned, that the features are co-occurring. Okay, so it will make your whole processing and computation easy as well. Okay, now question is how you will find this one, how you will find this distribution. If you find this distribution by this Chow Liu trees, hope so I'm pronouncing it right. So what does it say? It says you need to find this score between every feature z1 and z2. You will find like z1, z2, 1, 2, 1, 3, 1, 4, 1, 5, every word. Okay, you need to find this score between every pair of word. And what is this score? This score is probability of zi into zj log probability of zi into zj divided by probability of zi and zj. This I will give you the link of this formula in description as well. So what you will do is you will find scores on the basis of this chow liu algorithm. For example, you had 4 features, 1, 2, 3, 4, or 4 words. You calculated the score between 1 and 2 and it was found, let's say, 4. Then you calculated 2 and 3, between 2 and 3, and it was found 8. And then you calculated between 3 and 4, it was found 4. Now, if x, and then obviously you calculated the score between x3 and x1, and you wrote it here. Now there are some rules, okay, to finalize the which edge to consider and which edge to ignore. So you will obviously consider those edges with highest number of scores. You will sort it out in descending order, every score that you have got, and you will say, let's say I will consider until 5 score, where the score is 5. You will consider those edges, plus you will not consider those edges that are responsible of creating a cycle. If you have considered this one and this one, you will not consider this edge even if the score of this is greater than 5. Why? Because this is making a cycle. Okay? So this is the rule of this algorithm. So it says that the scores of these two are high. It means these two random variables or features are co-occurring together. So this was the whole point that we wanted to estimate here. So this is how you will find a distribution where the features will be dependent. Now these two are dependent, these two are dependent, these two are dependent. So you have made the thing easier for you. You have basically found this distribution that you always wanted to find. That not you, obviously, the people who work for this FABMAP. Okay, so again, when you will finalize this distribution, you will check its similarity with the actual distribution. If it is similar, then you will consider this one. Okay, now you have found a distribution which is similar to the actual distribution, plus it had the links as well that are telling you that those features are co-occurring. Okay, so here, okay, now the remaining navigation part. Let me rub the whiteboard first. Okay, so for example, a robot was moving and it was observing the environment. Now it need to do two things. First, localization, and secondly, mapping. When it was taking the first observation, it was basically creating a set of every feature that it observed in the environment, where this set is it consists of every feature up till now, or the whole vocabulary, and each member of this list is a random variable that can be either 1 or 0. For example, in its ith observation, it saw this thing 1 1 0 1 0 0. It means feature number 1 is present, feature number 2 is present, feature number 3 is not present, it is 0, feature number 4 is present, but word or feature are same. Don't get confused here. So this is how it observes the environment. Similarly, for the next observation, it will create another vector, another same type of set or vector. It will be z2, and it will again be similar to this type of vector, where each member represent a word, and the length of the vector will be equal to total number of words that are present in the vocabulary tree or bag of words. And zk will be the list of total observations up till now. K is, let's say, your current time, then up till your current time, or until your current time, how many observations you have saved or you have been through. It will be like this: z whole power k is equal to z1 plus z2. This type of k informations are stored in the form of zk. Now this is information. Second, how it is constructing the map. It is constructing the map like this: location 1, location 2, location 3, and this is LK is the set of all locations. Okay. For example, Okay, this is the path, and this is location number 1, this is location number 2, this is location number 3, and every location obviously is independent of the previous location because it is a new. It will not be like correct to say independent, but obviously it will be a new location. L1 and 2, and how it will be making sure that it is new location obviously based upon the observations. It will obviously it would have observed the environment. Let's say it observed while it was deciding that it is location number 3, it was observing LZ4, let's say. Okay, so it observed Z4, it observed fourth observation, and after observing it said no, it is new location. Let's save it as a new location here. So it is making this type of map by observing, and observation is done this way. So this is how it is making a map of your environment. Now the good thing of FABMAP is, as I said, it is not only saving the feature, but it is keeping the track of which features are occurring together. For example, it observed this brick on its path. So it had obviously, let's say it observed 4 corners of the brick. Now it will automatically, by obviously making this sure that these 4 are co-occurring features, it will automatically create or generates an event which is a brick. Okay, so it will automatically generate, oh, I have seen a brick in the environment. Similarly, why? Okay, so which, obviously it decided it is a brick based upon these show you thing that we did here. This thing is called event. So it will make events of every object that was responsible for creating, let's say, the map, or that was present in the observation. Okay, this is why, and it creates this event on its own. It generates the event on its own. Okay, by obviously using the information of the observation. Therefore, it is called generative model. Okay, and it is represented as this thing. Okay, probability of event 1 is equal to 0. Now this event has occurred at location number, let's say 2. Okay, it has found that at location number 2 it has seen this event. So whole localization, it will be more confident in localization then. Okay, oh, I have seen this place before. Why? Because this brick was there as well. Okay, maybe it will help in loop closure as well. Okay, and this is the whole thing. Then this is the little hope so you know about false positive and false negative thing. Okay, for example, probability of zi is equal to 1. It observed the environment, okay, and event was 0. Okay, in observation number I, it said it has detected something, but it was not actually there. Why? Obviously because your model was keeping track of your environment. Okay, your new observation said, oh, I have seen the brick, but actually according to the model there was no brick there. So what does it mean? Okay, actually it is 0, but you have predicted it 1. This thing is called obviously false positive. Okay, there was no event and you predicted it 1. Similarly, when your observer observed, okay, it missed an event, it missed an observation, but it was actually there. So this thing is called obviously it was actually there and your model missed it. So this is called, it is called obviously false negative. Why? It says it is negative, but it is wrong. Why? Because it is actually present. This is called false negative. This is called false positive. It is saying it is there, but it is not there in reality. So false positive. It is positive but false. Here it is negative but false because it is actually there. So this is some other formula. Baki, for keeping the track of environment and for updating the locations, equation is same. We will use same base estimation for location update, which says a new location, probability of new location given your environment is equals to prior belief multiply by observation likelihood divided by a scalar. ठीक है, तो here obviously they use a formula for this. So this is the whole working principle, let's say, how your FABMAP works. This was all, and it gave very good results when the agent was left in the environment with FABMAP. So it actually predicts very well. It gives very low probability when two different but similar locations are there. Okay? Where many actual same model fails to detect. Okay? You have taken a similar picture from here and a similar, let's say, a wall picture from here. Now even a human can get confused that these two pictures or frames are same, but FABMAP is like accurate enough to distinguish between these two places as well. So this was all about FABMAP. See you in the next video.